So now we're working on part 2 of lab 3, designing a 4-bit BCD adder subtractor with 5-bit output. In this lab we learn how to make a symbol in Quartus. So a symbol can be thought of as a component, and when we get this symbol made, it will become part of our library. Actually, it will become in the project subsection, and it will work the same as any built-in symbol. We can use it the same as any built-in symbol. We can use it on our schematics. Okay, so we can make a symbol, and we can learn how to make, and I have the documentation for that under lab help. We can learn how to make a full adder, learn how to make a 4-bit cascade adder, learn how to do a BCD addition with the BCD correction, and learn how to work with array variables and test bench with array variables. So what I want to do now is talk about the BCD correction. So I found a good reference on this here. So you can highlight this and do Control-C and Control-V into your URL line of your browser, and you end up here. Okay? So it's going to show you how to do the BCD correction in BCD addition. So he comes up with a BCD adder design. Okay, except he has a carry in here from a previous stage that we don't have. So we can turn this into an adder subtractor by just replacing this 4-bit binary adder with an adder subtractor, and we've got a design. So he's trying to derive the BCD detection and correction circuitry here. So the yellow part is the detection, and the correction is the add 6. So whenever the detection detects a need to add 6 for BCD correction, you'll learn that BCD correction involves adding 6. Then it activates the 2 middle bits to add 6. Okay, so let's move along to deriving this circuitry. So what are the BCD digits? They are, in this table, the ones that are 0 through 9, 0, 0, 0 through 1, 0, 0, 1. And the A, B, C, D, E, F are excluded. That's BCD. Okay, so when we add BCD to BCD, we sometimes get a BCD answer, sometimes we don't. So here we got 6 plus 3 is 9. That's valid BCD, so that's good. Now here we did 7 plus 5 is 12. Answer is not BCD. Okay, so the way of correcting this is to add 6 when you have an invalid BCD digit. So 5 plus 7 is 12. You get 1100. Add 6, you get a 0010, but that the full answer is not contained in 4 bits. You have an overflow. So that overflow gives you a 10, and you have 5 plus 7 is 12. Now here you have 9 and 6 is 15. Add the 6. You're going to get 5 with an overflow and get 15. 9 and 9. 9 and 9 is your maximum possible sum. It's going to give your maximum possible sum, 18. Here it says maximum answer is 19 because he is considering the possibility of a carry in for a previous stage. But your maximum result is 18. So we add the 6 and we get an 8. Okay, but there's an overflow, so the answer is 18. Okay, so we're going to derive the logic now to determine the need for the BCD correction. And here we have a table with all the possible 5-bit answers from the first stage of the addition. In our case, addition and subtraction. Okay, so we have a carry out in 4 bits. And you have all the possible sums. Okay, and some of them are going to need correcting. So the ones that need correcting get a 1 in the F column. Those need correcting. Now we could do 5 variable key maps, and we could get the equation for F, which is the overflow and detection circuit. But 5 variable K maps are cumbersome. So we're going to do what this author did, break it into 2 parts. Because we see that you have 2 situations. Either your digit in the 4-bit field Z3 through Z0 is invalid, or you got an overflow in the first stage. So we see an or between these two things. So we can break them down separately. So we derive an equation that lets us correct in the range 10 through 15, and then we OR that with the carry out. Okay, so it's done here with a K-map. So this K-map is based on a table with only 4 columns and only goes up to 15. Excludes the C out column. And then that gives us Z3, Z2, Z3, Z1. It detects the occurrence of a non-BCD digit in the 4-bit field C3 through Z0. So all we have to do is OR that with the carry out from the first stage. And we have the equation we need. And that equation is implemented in yellow here. Okay, now note that, I think, did I tell you this before or not? Yeah. So when the detection circuit detects the need for a correction, it sets the 2 inner bits for this operand to 1 to add a 6. When no correction is needed, then the output of this is 0, and you're adding 0. So it works perfectly. Now, the output carry is used as your overflow. Remember, your answers had an overflow. Look back here. See the 9 plus 9 is 18. It needed overflow. So that output carry, you can call that your overflow, OVF. And then you have your circuit. Okay, so that part's done.